Hi folks, here's some more Chapter 6 problems. A monkey is hanging by one arm and swinging from limb to limb. As the monkey swings, the bottom part of his path sweeps out a semicircular path. He has a tangential velocity at the bottom of his swing of 2.80 meters per second. The distance from the branch to the monkey's center of mass is 85 centimeters, and the monkey has a mass of 9.5 kilograms. What is the centripetal force acting on the monkey? So here's the circular path. Here is our monkey's arm, and here is his body. Okay, not the best monkey body you ever saw. And here is his little legs. There we go. And we'll give him little monkey ears. There he is. Okay. He has a tangential velocity of 2.8 meters per second. The distance from the branch to the monkey center of mass is 85.0 centimeters. To get that in MKS units, we're going to convert that right away to 0.85 meters. And he has a mass of 9.50 kilograms. What is the centripetal force acting on the monkey? Well, the centripetal force pulling him into that circular path is going to be his mass times centripetal acceleration. Well, centripetal acceleration, one of the equations for that is v squared over r. We have velocity, we have radius, so centripetal force can be mv squared divided by r. So we're going to go ahead and put the values in that. Centripetal force is going to be the mass, 9.50 kilograms, velocity, 2.80 meters per second. Square that quantity, the radius of 0.85 meters. Grab my calculator, and here goes. 9.5 times, open a parentheses, 2.8 squared, close parentheses, and divide that by 0.85. I ended up with 87.6 newtons. If I go to 3 sig figs, is the centripetal force on the monkey. Part B, what is the tension in the monkey's arms? Well, here's what's going on. There is a centripetal force upward, but the arm of the monkey also has to support the force of gravity downward. So the tension is going to be the combination of both of those. So the tension in the monkey's arms is going to be a combination of the let me make sure I get this right. The tension minus the force of gravity is going to equal that centripetal force. So the tension is going to be equivalent to the force of gravity plus the centripetal force. The force of gravity is going to be mass times acceleration of gravity plus centripetal force. Well, mass, we know we have a 9.5 kilogram monkey. Acceleration of gravity is 9.8 meters per second squared. And from the previous part, we're going to pull down the centripetal force of 87.6 newtons. And when we do the math on all of that, 9.5 times 9.8, this ends up being 93.1 newtons plus my 87.6 newtons. I end up with a grand total of, rounded off to 3 sig figs, 181 newtons is the tension in Mr. Monkey's arms. Okay, let's do another one. This one involves a force of gravity. If a 1 kilogram rock is sitting on the surface of the planet Mercury, what would be the force of gravity on that object due to the mass of Mercury? All right, we're going to use the force of gravity equation. Force of gravity is equal to G, mass 1, mass 2 divided by distance between their centers, squared. So we want to know the force of gravity on an object due to the planet Mercury. So the force of gravity is going to be equal to G, the universal gravitation constant, which happens to be 6.672 times 10 to the negative 11th Newton meters squared per kilogram squared. It is a 1 kilogram rock sitting on the surface of Mercury. What is the other mass? Because force of gravity, there's always going to be a gravitational tug between two objects. Well, the other object is Mercury. If you look on the planetary data table I gave you in the beginning of the course, the mass of Mercury is 3.18 times 10 to the 23rd kilogram. And the radius of planet Mercury is 2.43 times 10 to the 6th meters, and that radius down below must be squared. So now we're going to pull this into our calculator. These problems aren't hard, but you have to pay attention to scientific notation. So 6.672 to the negative 11th times 1 times 3.18 times to the 23rd equals, divided by, open parentheses, 2.43 to the 6th square, close parentheses, equal, and I get 3.59, that's a 3, if I take it out 2, 3 sig figs. Now, it's a force. It should be newtons. Let's take a look at those units and see what happens. I have kilograms and kilograms squared. So those 2 kilograms cancels kilograms squared. I have meters squared, newtons, hot diggity dog, we end up with newtons. So life is good. Let's see if we have the room on this video to do one more, and I think we do. Let's do a little comparison. Mercury is very close to the sun. So is the force of gravity from Mercury larger, or is the force of gravity from the sun larger on our one little 1 kilogram rock that we talked about in the last problem? What force of gravity does the 1 kilogram rock sitting on Mercury feel exerted on it from the sun? So we're going to use the same equation. Force of gravity is G, universal gravitation constant, mass of the first object, mass of the second, distance between the centers, squared. But to begin with, we are going to find out if this little rock is sitting on Mercury. We want to know the force of gravity on it caused not by Mercury, but caused by the sun. So the force of gravity caused by the sun is going to be G, 6.672 times 10 to the negative 11th Newton meters squared per kilogram squared. My 1 kilogram rock. But this time we're going to use the mass of the sun, 1.991 times 10 to the 30th kilogram. Our star is large. Now we're going to use the distance between the sun and Mercury. That's the distance we're going to use here, 5.79 times 10 to the 10th meters squared. And when I throw all that in my calculator, let's see what I get. 6.672 to the negative 11th times 1 times 1.991 to the 30th equals, divided by, open parentheses, 5.79 to the 10th square, close parentheses, equals, and I end up with 0.0396, if I take this to 3 sig figs, newtons. Which force is larger, the force from Mercury or the force from the sun? Now this is from the sun, and if I look back to my previous problem, the force from Mercury, the answer I got was 3.59 newtons. So which force is larger? Well, obviously the force from Mercury is much, much larger. How many times larger? So if I take the force from Mercury divided by the force from the sun, if I take 3.59 newtons divided by my 0.0396 newtons, let's see what happens. 3.59 divided by 0.0396, I end up with 90.6 times larger. So much, much, much bigger. When it comes to gravity, mass is important, but proximity is very, very, very important. That will do for that combo. We will see you later. Bye-bye.